Yeah, this week.
So only got 2 tracks, sir?
2 tracks.
Well,
We have many number of tracks, but then only 2 number of tracks for each student. One on overcurrent, one on distance. But that's just go and participate and then understand that sort of thing. Quite easy, straightforward. Join 8 3 1 7 5 6. Hi everyone, can you hear me? Yeah, thanks. Okay, Zoom, can you all see the slides as well? Yeah, thank you. Okay, so starting week 8. So we are starting some lab sessions this week. The labs are on overcurrent protection and then the distance protection. So please look at those lab sheets, and then you may have to fill certain numbers and then take some data from the experiment and then just publish it in your report, right? So that's why that the report is the submission day of the report is delayed until the end of the tracks. So once you finish the track, probably you will have better understanding about overcurrent and distance protection relays. And then the relays that we use is the relay, actually not relays. That is a numerical relay. So it's a market product. So you can go and then play with that relay as well. So you will have enough time to go through all the activities and then try to discuss with the tutor, like, you know, various other functions. If you want to find it out, that's fine. Okay. So as you heard that there's a holiday next week, I think. I don't know what what is the university arrangement for that. We will wait and see, right? And then, but the Friday we have the exam. So Thursday is the one that government has declared, but I'm not sure what the university arrangements are yet. So I'm expecting that a couple of emails will come through this week. Regarding the lectures that we started about discussing about instrument transformers, and then out of them we did some calculations related to the current transformers and then discuss how their behavior. Today we are going to look at the voltage transformers, or we call it as potential transformers as well. As you can see here, I gave you a brief description about them in the last class. If I recall, you can see that these VTs, they have only one connection from the supply, the other end is grounded. And then typically these VTs, they measure the ground to phase voltages. And then there are certain VTs which measure between the phases, but most commonly between the ground and the line, because the voltage levels are lower than between the lines. So there is no big difference between a VT and a normal transformer. It has a primary winding and secondary winding. Primary winding has more turns, secondary winding has less turns, so that you can measure the voltage as a lower voltage in the secondary side. And then when you are looking at VTs, typically the secondary side voltages are between 100 to 120 volts, which are measured by the relays, right? So the relay can measure safe level of voltages, while the primary side has very high voltages, like from, let's say, up to even not 500 kV, sometimes it's going now 1 megavolt as well, right? So it depends on the system voltage. And then the capacity or the power that the VT can handle is given in the VA ratings, same as CTs. Probably you can remember the couple of VAs for CT, but then typically their VA rating is higher than the CTs. So based on the VA rating, we have to decide what sort of load that we can connect across the secondary, right? And then the same VA rating, that it is another name for that is burden. We discussed these things in the previous section very in detail. Yeah, and then typically it is the accuracy of the VTs. Like, accuracy means that how correctly you can measure the primary voltage in the secondary side, because we assume that the turns ratio gives the secondary voltage, right? So, and then when once we measure the secondary voltage, we multiply it by the turns ratio to get the primary voltage, but the primary is different from that, right? So we have an expected primary voltage and then the real primary. So the difference between those two values are basically the error, and that error changes with the magnitude of the burden. So when the burden goes up, sometimes the power consumption by the secondary load, when it goes up, then the error increases. It's the same as normal transformer. Okay, so if you are looking at the standard VTs, again, there are multiple standard VT ratios. You can find it depending on the requirement, right? So all these are from one of the standards, right? So you can find it, like, you don't have to decide it by yourself. The standards will give you these other available ones, and then in the market you can find different ratios. Depending on the requirement, you need to get it. And then you can see that the dot, right? You can see that the voltage positive is towards the dot in both sides. That is the upper sign convention. When you measure the positive voltage, then if you measure it from the bottom end to the top end, then they are the two voltages, the input and the secondary, or the primary and the secondary, they are in phase, right? Remember that if you swap those two directions, or if you swap the direction of the secondary, then there is a 180 degrees phase shift between the primary and secondary. So we have to remember those points when you are really connecting a transformer secondary, because most of the time the phase angle is also another important parameter. So if you are looking at the type of VTs, we are looking at two type of VTs. In current transformers, we just had sort of a toroid where that you wounded the coil to get the secondary current. But in the case of VTs, you can use the normal transformer where you have a core and then two windings are in the core, basically coupling the flux produced by the primary is coupled by the secondary. So that is the general transformer. But then when you are going ahead with very high voltages, sometimes it is not economical to use these electromagnetic type VTs where you have just the turns, two turns. The reason is that the insulation level will go up, because when you have very high voltages, you need to maintain very high insulation levels. To avoid that, they have another design called CVTs. CVTs are called as capacitive voltage transformers. So capacitive voltage transformers means that the very high, extra high voltage is reduced to a reasonable level by a capacitive divider. And then that smaller voltage is fed to another electromagnetic transformer. So it's a combination of electromagnetic transformer and a capacitive divider. So then we call it as a CVT. So we'll look at first the normal electromagnetic types. So it's a very, very simple, step down transformer, nothing to, look at very specifically there, right? And only, see, it also has sometimes in the reality, you need to cool down these, losses created by this, magnetic, let's say material or losses in the winding. You need to do those things. So that sometimes these VTs, they are enclosed with oil bath, right? Enclosed in an oil bath. So that is very common practice. That's why that they are sort of that big column that you have seen in the transformer, inside it that you will have lot of oil, right? And then one end of that coil, the big bushing, it's a sort of a oil bath where that you have these windings immersed. And then the winding, as we know that the number of windings or the number of turns in a winding, that is proportional to the voltage that you apply, right? So it is very like N1 to N2 is equal to V1 to V2. So it is the very fundamental. Oops. So here, if we have V1, here if we have V1, V2, N1, N2, the turns, so V1 divided by V2 is equal to N1 divided by so that is the normal transformer ratio. Okay, so that is simple. We don't have to talk much about it because this has been covered in many other courses. The other thing is this one, capacitive type CVTs. So to reduce the VT size and the cost both, you introduce this technique. And what we do is that you can see that this part is called the capacitive divider. Right? So what divider is doing, it reduces the voltage, like let's say from V1 to or V primary to V1. Right? So it's reduced significantly. Therefore, the insulation level that is used in this transformer is now low. So that is quite, and then the other advantage is that when you are having, like let's say if the transformer operating voltage is very high, then the size of the transformer is also increased or big. It's a big transformer. Then we can reduce the size by doing this technique. And then now a smaller voltage applies to this transformer, and then we measure the voltage at the output, right? So here 110 divided by square root 3, the reason is that the line voltage is 110, but what we measure here is the phase voltage, right? So this sort of arrangement is quite common in extra high voltage arrangements, like above 220 kV, very, very common, right? So there are some other advantages of this as well. If you can see here, these are the typical CVTs, right? When you have this sort of, let's say CT, the capacitive divider, the extra advantage of it is that you can, let's say, we know that impedance of the capacitor is very low for low frequencies or high frequencies, very high frequencies, because impedance of a capacitance is ZC is 1 upon omega C. So if we feed a very a signal with very high frequency compared to the power frequency, then we can send it through this system because the capacitor impedance is low. Now the 50 Hertz or other frequencies, lower frequencies, it is blocked. But that particular frequency, you can create a resonance at that frequency using this system, right? So if you feed that signal to this system, then you can send that signal through the stem wire without disturbing the normal power. And then we can filter it out because for that particular frequency, this capacitor impedance is smaller. So now that is what is called as power line frequency or PLCs, power line communication, so that you can send the communication signals through the power line other than the power, so that the information going from this feeding here in this to this let's say through this VT, you feed the information to the line, it goes to the other end, then you have to get it back. But see, the one of the requirement here is that you can't jump through a transformer, because for a transformer, for high frequency, impedance is high. Therefore, that PLC, the power line signal or power line communication signal, it's not going through the transformer. Transformer is a sort of it's blocked, right? So usually this communication is in between two locations before the transformers. But if you want to go through the transformer, then there are techniques. You bypass the transformer for higher frequencies, right? There are ways of doing it, but typically it is easier to transmit the signals between the 2 points before a transformer is connected to the system. So this is some sort of a way of doing this this sort of thing. You can see that this is the high voltage transmission line, right? And then in the right hand side you can see a real VT, right? This is a real voltage transformer, right? And then inside this box that you have the windings, and then this column is bushings, and that is to get the sufficient insulation between the live and the ground, right? And these are the terminal box where that you have the access to the secondary terminals, and also not only that, communication terminals. So you can see here, this is the coupling capacitor, right? And then you, under the coupling capacitor, you have something called line tuner, and then using a coaxial cable, you connect it to the transmitter and the receiver, right? So that's the arrangement after this point. Okay, so this is the coupling capacitor inside this CVT, and then you feed the signal to one end of it, so that say this side is high voltage and then this side is low voltage. So you feed the signal to the low voltage side, and then because of the low impedance it goes to the line. But then another important thing, you can see that these sort of line trap, have you seen these sort of line trap? Probably if you go into in some substations, you will see this strange thing connected to the lines, right? Some small gadgets. So one of them is this line trap. Why do you need the line trap here? Because this signal, we need to let's say we need to avoid it's going into this direction, but we want to push whole signal towards the other end here. Then we need to find a mechanism to stop that signal going towards this station A direction. So that's why that they put line trap. So line trap is some sort of a impedance which stops the higher frequencies, right? Especially the frequency that you are feeding here. And then you need the same sort of setup in this end, right? And then the signal flows through this, and then you can collect that signal through this the CT or the CVT at the other end of the line. So this is very useful application of CVTs other than the protection measurements, right? You can use it for communication, and then definitely that communication is useful for protection as well. Sometimes that you need to communicate between the protection systems in the two substations. You can use PLCs, right? Sometimes we use microwaves. Sometimes you can use, nowadays optical fibers are used. So all those different techniques. I mean, these mechanisms were available even before optical fibers came through. How does it operate in reality, like this sort of CVTs? So you can see that this is the A is the point where the live point, like the power line voltage, high voltage, and then the VB is the intermediate voltage. So how do we obtain? If we look at the Thevenin equivalent across these 2 points, right? If you are looking at VTH and ZTH, that's what we need to look at. How do we develop the Thevenin equivalent? You remove the load side and then look at the source circuit here. So if you remove that, then so across this, okay, B and C, right? A, B and C, right? So across these 2 points that I need to find VTH and ZTH, right? It's quite simple, because what we need to do, we have to find the open circuit voltage. Open circuit voltage is the voltage at B. What is the voltage at B? Because the voltage at this point is VA, right? That is the supply voltage. That divider will give you this voltage. So we know that this is C1 and this is C2. So C1 multiplied by VA divided by C1 plus C2 will give you the voltage P. That is the for a capacitor. It's not the other way of the resistors, right? So other way of the resistive divider. So once you have that voltage VB, then we know what is the VTH. To find ZTH, you can take 2 different approaches, but I took the one with finding short circuit current between, right? If I find the short circuit current here, which means VA divided by this impedance of C1, because the current will go through like this. There is no impact of C2. So that I short circuit current between B and C is voltage at A divided by 1 upon j omega C1. That is the impedance, and that is equal to this. So once you know 1 and 2, 1 divided by 2 will give you the impedance, VB divided by I short circuit. So that is the Thevenin equivalent impedance. So once you have the Thevenin equivalent impedance, then we can represent this whole system like and then if you go back, the rest is the inductor and transformer here. Right? And then this one is ZTH and this is VTH. Right? So once you have that, to apply the same voltage, that we know that ZTH is capacitive, transformer is inductive, oops, right? So if the transformer is inductive, Thevenin equivalent impedance is capacitive. To get the same voltage of VTH across the transformer, ideal transformer, this part is the ideal transformer, right? And this is the impedance or inductive impedance of the transformer, right? And then I have neglected the magnetization branch here, right? Now, if you want to get this, because what we want to say is the voltage what we measure at this end multiplied by some constant will give you the primary voltage. So then I don't want a voltage drop across this system. I don't want a voltage drop across this system. When you have applied VTH here, I want the same voltage across the transformer here. What is the, how can I achieve that? Like how can I avoid this voltage drop?
By balance.
Basically, the capacitive impedance should be equal to the inductive impedance. Then the total impedance becomes 0, which is basically, we call it as resonance, right? So that is what we have done here. See? This impedance is 1 upon j omega C1 C2. J omega L is the equivalent transform impedance. And then once you make it equal, then you can see that the inductance is equal to 1 upon omega C1 plus C2. Now, using this, we have some sort of a relationship between the transformer and the capacitor values. So which means that at this, using this relationship, we can select the appropriate capacitor values and inductor value for the transformer. So that is how that we try to so that to avoid or minimize the errors in the measurements, because if the measured voltage here gives a some value which is not, let's say, proportional to the primary voltage, and then not by, like, let's say if you can't calculate the primary voltage by multiplying some constant, then it creates an error. So that we can reduce that error by using this technique, avoiding voltage drop on this line, right? So that is the technique. We will have some calculations related to that in the tutorial. So you will see how to select this C1, C2 and L using this concept. Then again, that we need to look at the errors, right? Errors is we want to minimize the errors when we do the measurements, right? So how do we do that? First we need to define what is an error, right? So for a CT there are two types of errors, because if you are looking at the measurement of the secondary side, the magnitude that you measured is not the expected one, therefore there is a error. And also if they are out of phase slightly, like we expect that primary and the secondary voltage should be in phase, but then if there is a small angle, 1 degrees difference or 0.5 degrees difference, then that is the error. That error is called as phase error. So you will have magnitude error plus phase error for a VT. And then how do we find it? This is the same as for a CT. You can see that primary voltage divided by a number, that is my expected value. The Kn is the ratio that we use for that VT. So Vp divided by Vn is my expected value, that is what I want, right? But then probably Vs is not the same. If the Vs is same, then we don't have any error, right? With respect to the measured secondary value gives the ratio. So you take expected value minus the what you have measured, divide by the what you have measured. So that is the typical equation for a ratio error for a voltage transformer. And then when you are looking at the phase errors, how do we define which direction is positive, which direction is negative? Because phase error could have a leading angle or lagging angles, right? Say if this is the primary voltage and then if the secondary is like that, so now what we say, this is delta is the error, but then secondary Vs leads primary Vp, therefore delta is positive, right? That is the definition. So if the secondary leads the primary, then you call it a positive phase error. The lagging, you call it a negative. And also there is another interesting way of, if you look at the standards, this ratio error and phase error both of them are given in as a one figure, like this one. So usually say that the transformer had a 1% error. 1% error means that is the magnitude is also 1%, but phase is also 1%, right? How do they interpret it? That is how what is described. Say US is the measured secondary. This is the expected secondary because this is the turns ratio and this is the primary voltage, but you can see that they are not in the same phase, and then slight magnitude error is as well. So U delta U is the magnitude error. Now what we do, right, assume that delta U is very, very small compared to US. Delta U is very, very small compared to US. Why? The secondary voltage, let's say if it is 5 volt, or sorry, 120 volt, the error might be 1 volt, right? So it's a very small value. Therefore, first what we do, we try to look at how do we develop some sort of a percentage value here. So we divide all parameters by US. Okay, and then we multiply it by 100%. Then we ended up with this sort of figure, right? So it's the same thing as what I have done, divided every parameter by US, multiplied it by 100%. Now look at this figure, right? We know that this distance, right, from, let's say, based on this becomes now 100%. Right? What is this distance then? From, if delta is in radians, this distance delta, okay, this distance, right, that is basically delta times 100%. Got it? Because this is 100%, r theta will give you the distance, right? So this is delta times 100%, right? Delta is my error, and then this is also equal to, because this distance and this distance are quite similar, because when your radius is large, then this difference, the difference between these two vectors becomes smaller, right? There is an error, but then this one and this one is almost equal, which means that now here the magnitude error is also, let's say, certain percentage error percentage. So I will call it as error times 100%, right? So you can see that these two are same. So once you say 1%, it means that magnitude error is 1%, delta is also 1%. Delta 1% means that 1 centiradian. That is what we need to understand, right? This is error is in the radians. 1% means 1 centiradian, right? So which is equal to 0.01 radians. So if it is 2%, which is 2 centiradians, right? So that is the so you need to, if you want to convert it into degrees, then you have to convert this 0.001 radian into degrees, right? So 34.4 minutes is the corresponding value. Okay, so it's that this method is easier to, like, let's say when you are looking at from the practical point of view, it's easy. You don't have to provide a lot of information. Then 1% error means magnitude and the out of phase errors. And then when you are looking at these VTs, usually they should have a very reasonable accuracy from 0 to 173%. Right? I will count by 173%. If you look at what is the value of square root 3? Can you find some similarity here? Yeah? So what it means that during a fault, ground voltage, the maximum level of it depends on the grounding mechanism, but the maximum voltage of the ground voltage or the phase voltage is equal to line voltage. That is the maximum value that it can reach during a fault. So that's why that within this range it should have good accuracy. So because it is under the fault, it should work properly, right? Usually for a metering purposes, as I said before, the accuracy is high. Protection purposes that you can have comparatively less accuracy. Yeah, so and the other thing is that accuracy is not the primary thing which decide the cost, but for a CT, yes. For a VT, no. Right? There are other factors like voltage levels and then whether you are using a communication channel with the VT and those sort of other things, right? But because transformers are anyway very accurate, right? They are not basically inaccurate devices. The other thing is that the accuracy of measurements, those depends on the type of the load you have connected across the circuit, because that will introduce load. Because of that, you introduce an error. So that is a more prominent error than the error accumulated by the transformer itself. So these are two ways of explaining this accuracy. You can see that the secondary, this is the primary side of the transformer. It is across the ground. And then the secondary side, I have connected two loads. The load 1, you can see that it is 30 VA meter burden, which means that a meter measurement, which is not for the protection, that's power consumption is 30 VA. And then the other load is 170 VA, which is the relay power consumption, but that is connected 100 meters away, right? This one is also 100 meters. So why the distance is the same? Because in real life that all equipments are placed in your substation control room, right? Control room is in one location, right? So that we need to have the same distance. But then can you see that in this one we used 2.5 square meter cable, this one 4 square meter. The reason is that this one has higher impedance or higher resistance, this one has lower resistance. So when you have a higher resistance, when you go along the line, the voltage drop is smaller. But in a lower one, right? Sorry, if the lower impedance, for the lower impedance, the voltage drop when you go along the line is smaller. But if the impedance is high, then the voltage drop in this line is high. So that is why that even though the load is higher or load is lower here, still we used a low resistance wire, right? So the reason is that you want to reduce the voltage drop because this is used for metering purposes. So in reality, usually for this sort of setup, total voltage drop here should be less than 0.1%. That is general requirement. It shouldn't be more than 0.1%. So if it is like, let's say more than 0.1%, then you need to change the type of wires or you need to change the relay burden to improve the connection times. And then the other important thing is that when you have, let's say, protection relay and metering, we are not connecting them to the same line. Like as an example, another cost-effective way is that you connect this one here. 170. That is another way, right? Parallel connections. Low cost, right? But this is a wrong configuration. The reason is that it works, but then if you are using this with the metering, and then if you are using it with the protection, you don't want to use this two different things in the same circuit. That reduces the reliability, right? So that's why in typical substations you will have two separate connections, so that there is no interaction between the protection part and the metering part. Okay. Yeah, in this one, see, you can see that, like, this is just an example, right? Forget about these drop percentages compared to this one is very high, right? But then you can see that for the relay, this is about 3.05% voltage drop. For the metering, it is only 0.33. So see the difference. And then if you are using that sort of voltage drop for metering purposes, then that affect your revenues, right? But for the protection part, 3% difference even, that you can survive with that, right? Because anyway, the voltage changes will be very large, or the current changes will be large, and then the protection is just to detect abnormal conditions, not for sort of identifying the cost associated with, energy dispatch, right? This is another figure showing that how the voltage drops with different size of wires. So you can see that for the same load current of 3 amps, then if you use 10 square millimeter wire and 6 square millimeter, so voltage drops with the distance. And not only that, usually for these sort of circuits, secondary circuits, we use fuses, right? We need to have fuses, because if the secondary circuit is short circuited, there is no other way to protect it, right? Because it doesn't have any impact on the primary side, right? The primary side is pushing a lot of power into that, and then if you short circuit the secondary side, then there will be a huge current flow, and then your secondary side of the transformer will be damaged. To avoid that, you need to put a fuse. But once you put the fuse, that introduces a burden as well, because fuse has its own resistance. So if you look at here, see different type of fuses, that they will have different resistances, and then that gives you a certain voltage drop as well. 16 ampere, 10 amp, 6 amp, and then when the amperage is higher, the voltage, the resistance value is lower. Therefore, lower voltage drop. Right? So one needs to think about all these things when they think about the burden. Wires, fuses, and meters. So those are the main points. There's a small class exercise which I will do usually on my Friday tutor session, just before the tutorial, right? Yeah, as I said before, voltage transformers can be connected interface or between phase to earth, but CVTs are typically phase to earth, because CVTs are going with very high voltages, and then very high voltages, if you connect something in between phases, it will increase the voltage further. So to avoid that, usually CVTs are typically phase to earth. And then also they are, in the secondary side also, they are grouped, like as in the primary side, we usually send not single phase, they are 3 phase. And then when you are dealing with the 3 phase, secondaries are also grouped in different ways, like this. Like as an example here, the secondary is now what connection is? It's a Y connection. And then it can be delta connection as well. But you can see that even in the delta, that you have a ground connection. One point is ground, let's say, Here it is easy, the neutral point. But here you need to connect one of these faces to the ground. The reason is that is for the safety. Secondary circuit should be earthed at a single point, not in multiple points. Right? That's very important for protection, the safety of the system. Right? It is in this case, what happens is that your one of the voltages will be 0. But here, the neutral point is ground. Right? So in this delta connected system, you can see that primary is not grounded because we don't know. We can't ground it, right? It's a system. But in this one, still this point can be grounded because these transformers are connected in Y, and therefore the neutral point, this one is not connected to these lines, right? That point is the neutral point. Therefore you can ground that. Remember? Like in this one, that you can't just push this point into ground because this is the phase voltage here. Okay? So, but secondary, it's a must. And then when you have these sort of things, and then sometimes that we use these different type of connections as well. This is called open delta connection, which means we can reduce the number of windings or number of transformers. You can say here, I've used only 2 transformers. And then what does open delta means? A to C connection is now open. There's no connection there, A to C. Right, see? A to, this is A to C. And then A to C, ideally there should be a winding, but that is open. Right? And we only monitor the voltage from phase C to B and P to A. Right? It's only those 2. So these sort of arrangements is quite useful to detect line faults. But it's really hard to detect because between the lines, if there is a fault, voltage drops. That will be reflected here. But then the other important thing is that in this sort of connections, that you will see that the 0 sequence component doesn't exist. Line to line measurements, the 0 sequence measurement doesn't exist because the ground is not there. Right? And then the secondary, definitely you can see that one point is again grounded, right? Because you need to ground one point. And then the other connection is called broken delta. This is open delta, this is broken delta. Because you have the 3 transformers, but one end of the delta, it is not coming back and then connected to because delta has to be closed. See, this is the close point, right? I'm not going to close it. Instead of closing it, I'm measuring the voltage across it. So why? Because if there is a 0 sequence component, then that voltage, this 3V0 should have some, let's say, some value, right? But if there is no 0 sequence, if there is no 0 sequence, then addition of these 3 voltages will be equal to always 0. So that this is the very, very easy way of calculating the 0 sequence. You don't need any mathematical modeling or anything, you just measure the voltage and then see, oh yeah, the 0 sequence is there. So, as I said before as well, to protect the VTs, you need to have some mechanism. The mechanism that is proposed here is that putting a fuse. A fuse will reduce the secondary winding current. But then, can we stop, let's say if there is a short circuiting condition in the secondary, what is the impact on the primary side? Let's say you are supplying, 100 MVA, and then you just take a couple of VAs from this, and then your secondary side of the VT is now short circuited. What happens to whether the transmission line is going to be, melted? Is it? If you short circuit the secondary side, what happened to the primary? Primary, I'm not talking about the primary of the transformer, I'm talking about the whole system. Can you detect it in the primary side? Ideally, yes, right?
If there is no connection in secondary, then you
Can you detect it in the primary circuit? Like let's say you have 1000 amps current is going through the this one, and then you just short circuit the secondary. If you short circuit the secondary, then what will be the something, in a transformer secondary current? Probably it will go to 100 amps, right? Max, right? And then because I'm not, it's a system where the transformer is now in a let's say with a lower power. It's not a power transformer, right? It's not a power transformer. It's a voltage transformer with a lower let's say power level. Once you short circuit this, then what happens to the core? Core starts to saturate, right? Once the core starts to saturate, then there is no relationship between the primary and secondary, and then you can't detect it in the primary side. So that's why there is no way that you can't just put a fuse in the primary side and say that I can avoid I can identify the secondary issues. No. So in a VT, that is why secondary winding is the on because because of that, usually the secondary side you need to have a fuse. That is very important, right? Yes, it's what it says. It creates only few amperes in the primary, and it's not sufficient to rupture the high voltage fuse. So you can put a high voltage fuse, but nothing happens in that side, right? You can look at it in another form, another way. Say, right? This is N1, this is N2, right? And then this is I1 or IP, this is I secondary. IP divided by IS is equal to N2 divided by N1, right? Which one is large here? N1 is very large, right? So I primary is equal to N2 divided by N1 times IS. So very small vary multiplied by I secondary. If you look at it in that form, still the primary is a very small current, right? So by short circuit in the secondary, you will not be able to detect it in the primary side. So that's why those transformers need low voltage fuses in the secondary. So these are the typical, again, the values of fuses that we use. And then if you are looking at the accuracy classes for this based on the IEC standard, they have different accuracy classes for different purposes, starting from laboratory to the protection, right? So you will see that very, very high accuracy is required for lab work, right? And then precision and revenue measurements, the next one. Why? Money is involved, right? Nobody wanted to pay more, nobody wanted to charge more, or nobody wanted to lose more, not charge more, right? Nobody wanted to lose, nobody wanted to pay more, right? So then you need to have some high accuracy, right? And then standard revenue measurements, 0.5. So these are precision and revenue, right? And then industrial grade meters, 1%. And then instruments, this is the instrumentation, 3%. Protection, it could be 3 or 5, depending on 3-phase or 6-phase, 3P or 6P classes. There are different classes they define, right? And then when you are looking at the burden, burden must be maintained in between these different values. Those are the percentages, 100% to 25%. 100% is defined, like let's say defined maximum burden for that transformer, and then it should always work between 25 to 100, not even below that. And voltage, this is phi to Vf, means that 5 volt to voltage factor. I will explain what is voltage factor. That is the voltage of a certain factor or certain number multiplied by the rated voltage, right? So 5 volts to voltage factor. I will explain this in the next slide. And this phase displacement error, you can see that it is also increasing here, 120 minutes, which is 2 degrees, right? So it's, protection is very sort of relaxed from the error or the accuracy point of view. What is voltage factor? Usually different standards define a factor, right? For certain errors, what it says is that the voltage across the secondary of this transformer shouldn't go beyond this voltage factor, right? So as an example, IEC specified that 1.9 for systems not being solidly earthed, which means that if the system is not earthed, the VT should allow to measure measurements with a reasonable accuracy to 1.9 times the rated voltage. But if the secondary is earthed, then it is only 1.5. So to reduce the, let's say you can use a transformer with less cost if the system is, the neutral is completely earthed or solidly earthed. And also that it is very important to specify how long that the voltage transformer should be capable of measuring that voltage. How long, how far, right? Because let's say sometimes some faults, it could be there for hours, right? Until someone is going and fixing it, right? Like one transmission line is down and then the voltage of one line has gone to line voltage, and then that will be there for a while until someone goes there and then fix it. Therefore, when they define this voltage factor, they define some sort of a duration as well. So the duration, if you have an automatic fault tripping, then the duration is 30 seconds. So that the transformer should be capable of measuring the voltages accurately up to 1.9 for a solidly earthed system, and you should be able to measure it for 30 seconds if there is an automatic fault tripping. But if there is no automatic fault tripping, then you need to maintain that for 8 hours. So those measurements should be done for 8 hours. Once the voltage goes up, which means that if the transformer is not properly designed, then the transformer losses will be up, and then you need the cooling mechanism, and then because the temperature might go up, and then a lot of other issues, are there. So under those conditions, then 30 seconds is quite easy to maintain, but if you want to maintain 8 hours, then you need to have a proper design for it. So that is another important thing, right? How long that one needs to maintain that under abnormal conditions. And then the other important thing is that when the voltage reaches to voltage factor, that is 1.9 or 1.5 times the rated, the core must not saturate. Why? If the core is saturated, then you can't measure the correct voltage, right? Therefore, under these faulty conditions, core should not be saturated. So when we are selecting, by considering all these factors, when we consider selecting a VT, we need to consider these many factors, like what is my application, and then what standards I need to go ahead with, and then the type of the VT, whether CT or induction type, and then another one is the insulation level and altitude level. Why this is altitude? because this has some impact on insulation levels. So if you look at high voltage insulations, then when you go further up, above the 1000 meters, they have defined it in the standards above 1000 meters that you need to this, below 1000 meters you need to this, right? The reason is that with the pressure, air pressure, and then basically the pressure levels in the atmosphere, that will have some impact on the flashovers and a lot of other, and then the performance of the insulation, right? So that's why this is important. And then of course primary and secondary voltage levels, VT ratios, voltage factor, burdens, pollution levels, right? A lot of other things need to be considered, right? So when someone is selecting a VT, all these factors has to be considered and then go for, okay, this is the one that I'm going to use, right? It is not just the voltage ratio. It is just not the burden. You need to look at other factors as well coming from the atmosphere, the issues coming from the atmosphere or applications, and then, pollution levels, these sort of things are quite important, okay? So I'll stop there for a couple of minutes and then I will start the next part. Any questions in the meantime?
How can the pollution be like?
Pardon?
How can the pollution be the factor?
If the pollution is high, what happens is that, let's say if high salt conditions, right? And then salt deposited on the insulators. And then your creepage or the distance along the surface is now reduced. Like, the impedance is now lower. And then there will be high leakage current. So that probably you may have to use different material, or you may have to use as the insulator, or you may have to use a longer insulator materials, right? So those sort of factors, right? And then not only salt, but let's say acids, right? So if the environment has high acid level, industrial zones, then definitely you have to go for different. Otherwise, that very regular flashovers will be seen, and then that could damage the whole VT, right? So those sort of issues. Any questions, Richard or Thomas? Okay, thanks. Okay, we'll start a new section now. I'll continue this probably this week, and then if I can't, because next week, I think Monday, we have a industry lecturer. So I would expect that some of you guys will be here. Okay, so please come and then interact with these sort of people. That will be on next Monday. So if I can't continue this if I can't finish this section by today, then probably if Friday first part, if I have time, then I'll try to finish it. Otherwise, we may have to wait until even after the, I think, break. The first lecture will be given by industry lecturer. So it's, so to avoid the delay, I'll just continue it on Friday if I have time. So that's it. Quickly go through it on Friday as well. Okay, so what we are going to look at is now protection of certain components, right? We start with one of the important ones called bus. So probably because the next week, the industry lecturer will cover the transformer protection, and then someone will talk about feeder protection, right? Another industry lecturer. So then during the rest of the course that I will try to cover some other protection schemes like generators is there, right? And then I want to cover a little bit about the issues associated with renewable integration, things like that. So, but out of them, one of the most important thing is bus protection. I will come to the point where that what is bus and everything. So we usually bus bar. What is a bus bar? Usually all incoming and outgoing feeders, they are connected to one single bar. So a lot of power is associated with this bar. The reason is that, say if you have multiple generators somewhere else and then power is taken to this bus substation, it's connected to this bus. And then definitely slightly different from this in the reality that there will be some low voltage bus sector and then the high voltage bus, things like that. So usually these feeders, they are and then the supply to the substation, they are two different voltage levels, right? So I would say this is very generic module, but then if you are looking at high voltage or say substation, then the incoming feeders are connected to one bus, outgoing of ones are connected to another bus. Between these two buses, there is a transformer to reduce the voltage level. So, but what I need to say here is that you can see these sort of huge buses connected to, located in the substations, right? And then this is one configuration. This configuration is also available, but you can see the outgoing buses, they are connected to different transformers, right? And then these transformers will drop the voltage and then take the power out. So now let's say, since two generators are connected to this single bus, the amount of power associated with this bus is huge, right? If there is a short circuit of this bus, then it's much higher current than short circuiting one of these lines, right? So that is, and then the other important thing is that many feeders are connected to the same bus, which means that you need to have very high reliability. If there is a fault on the bus, all feeders are gone, right? So therefore, the bus protection is one of the most important protection schemes for a substation. And then in reality, they looks like this. See, these are the buses. Okay? These are the buses, multiple buses in this. And then of course for 3-phase, you need to have 3 buses, right? And then see, this is another one. So they are sort of huge aluminum type conductors, right? And then a lot of wires are connected to them, which carries the power from the generators or going out from this substation to the transformers. So there are many different bus arrangements, so that the protection schemes are different for these arrangements. Therefore, first we will go through what are the available the bus arrangements, and how have they connected in the substation. So so the 6 types are called as is, which I will go through one by one in the next couple of slides, right? Single, main, double bus, double single, breaker and ring bus. So they have, let's say why you have different options, because cost wise they are different, right? Some of them are very expensive, some of them are cheap, and then reliability wise they are different as well. So that in a system, if you want to achieve certain targets, like I want to maintain the cost at a different level, or I want to have this reliability, then you need to go for these different approaches. Okay, single bus, single breaker, very, very simple. So what it does is that, see, this is the bus, and these are the feeders. Like it could be outgoing or incoming, everything together, right? And then what we do is that you can see that you measure the current in each and every feeder. If there is a difference, why there is a difference? If there is a difference in the addition of these currents, why that difference is there? Because there is some issue in here. Because if, let's say, if there is a fault current going through the ground here, then addition of these currents will not be equal to 0. Otherwise, all of them should be always equal to 0. So what it does is basically, if it identifies the current is difference in addition of the current has some significant value, then it will trip. It will trip in a way to disconnect, or it will disconnect all these lines from the bus. All these lines. So that incoming and outgoing, can you see that? Because some of them, there can't be only just outgoing, right? Someone should bring the power to the bus, so that this will be done in both. So which means that all buses, all lines, or all feeders connected to that bus is disconnected, right? And which is good or bad? Bad, right? It's minimum flexibility. You can't just run even like, let's say, half of the feeders, right? So which is basically means this is not very common in distribution, transmission systems. They use it in distribution. The transmission system, this is not going to work. Then couple of feeders, like let's say you are bringing, thousands of MVAs to a bus, and then suddenly you disconnect the whole thing, right? Which is not going to work, and then whole system will be collapsed. So, but somewhat common in this thing in the distribution system, because distribution systems probably a couple of feeders are going into suburbs, right? And then probably if this bus fails, then all those suburbs are not getting power, right? But that doesn't mean that whole Brisbane is going to not to get power, but only certain small area of Brisbane going to lose power, right? So therefore this is common only in the distribution. And then there is another one called main and transfer bus, which means that instead of, like, this is the normal bus which is all the loads are connected, and then all the generators. But there is another one which is called a transfer bus, right? And then there are 2 buses now instead of 1. You can see that NC here means normally closed. NO is normally open. So you can see that these ones are normally open, these ones are normally closed. So you can clearly see that the load of any feeders, I would say feeders, the feeders are connected to the main bus here, see? Because they are normally closed. And there is a connection between the transfer bus and the main bus. they are normally closed as well, but this circuit breaker 52, which is normally open, so that these two are not connected. But then if it is required, it can quickly connect this. If you connect this, the advantage is that, say these are normally open, but if you connect them, and then you can supply power from both buses. So the two buses are sharing the load. And usually this sort of mechanism is useful when there is a maintenance in this bus. Let's say if there is a short circuit level, what are these? These ones and then 52s. These ones are, what are those? These are circuit breakers, 52s. These are isolators. So they are not automatically operating. Circuit breaker is something that automatically operates. So what happens is that since they are normal open, say if there is a fault here, these guys will operate, right? And then this bus will be disconnected, main bus. But what happens is that after that, since this is operating, now you can, these normally closed ones, you can open them, and then you can close these ones, and then the power is now supplied from the transfer bus. So it's not automatically, but you have time to work on this main bus and then fix the issue, right? It's not automatically transferred to this one, but still you have the some sort of a flexibility. And the other way is that, see, if you close this one in a critical condition, if you want to really provide some sort of a good power here, like reliability, then you close these ones. Now what happens? The power is going through both buses. During a fault in the main bus, all of these circuit breakers will be disconnected or open. Then again, the power is going through. But the problem with this transfer bus, you can see that there is no circuit breaker associated with that, right? If something goes wrong here, so that it is not a main bus, which is just for a certain small time duration, you can provide power through them. Okay, so it is not a permanent solution. Still, all breakers will be tripped during a fault. This is called double bus double breaker, very reliable. See, you have bus 1 and bus 2. These are breakers. The squares are breakers, okay? These are 52s, all of them. This is also 52, right? Circuit breakers. Now, you can see that these breakers, they will operate individually. Like as an example, if there is a fault on the bus 2, these breakers will disconnect the bus. But you can see that still this guy can provide the power. Very reliable, right? High operation flexibility. But what is the problem? The cost. For every feeder, you have to use 2 circuit breakers. Circuit breaker is an expensive device, very expensive device, right? And then you may have to have services, operational maintenance, and a lot of things, right? Pardon?
The load should is double. I think bus 1 should have a double load. As the load shifts here, the bus ratings will be high.
Yes, because this height should be capable of supplying the full load, right? So the rating of this guy is high as well. And like in usual operation, they are operating at 50%, right? If the lines are full load, then they are operating at 50%. So yeah, and then very expensive configuration, right? The line portions here, they are not protected by these circuit breakers. It's protected only after this CTs, this portion. And then here, it is only up to this portion. But then this portion is protected by line protection schemes. That's why probably if you go back and then look at, I mentioned about overlapping protection zones, that comes here, right? So zone protection will look after these areas, right? But then the circuit breaker or these CTs, they are looking after faults here from the top one above the CTs, for the bottom one below the CTs. Remember that, right? This is another one, double bus single breaker with a bus tie. So this is another configuration, right? Each feeder has one breaker, and then what they do, some loads are connected to bus 1, some loads are connected to bus 2. Can you see that? This is normally closed, normally closed, normally open, normally open, normally open, normally closed, right? So the last one is connected to bus 1, one before the last one which is connected to bus 2, likewise, right? So now the two buses are also disconnected here using the bus tie. Now what happens? If there is a fault somewhere in this, one of these buses, the corresponding line will be disconnected, bus tie will open, then some of the loads are still connected, but the loads connected to this particular, the loads connected to the bus 2, they are now disconnected. Now what you can do is that after some time, if there is a big issue, then you can connect those loads into the bus 1, but that's not automatic. But then you are not losing power for some customers, and then you have the flexibility there to bring it back to the power by quickly using the other bus, right? So this is, the bus 1 is like, let's say, not like that transfer bus, right? In the transfer bus, that you can't run things for a very long time duration because there's no proper breakers connected to that. But in this one, still the breakers are there. Therefore, you can share the load, you can operate both buses in the similar way. This is common in transmission and distribution, which is it's cheap, right? This is a very common one with very high reliability. It's called breaker and half, right? So breaker and half means that, let's say, if you count the number of feeders, let's say each feeder will have 1.5 breaker. It's ideally, it's not, you will confuse that up. How can you put up 1.5? But the configuration will give you that, right? So number of breakers is equal to, say here, 1, 2, 3, 4, right? So then you will have 6 breakers, 1, 2, 3, 4, 5, 6, right? How does that work? You can see that between the bus A and bus B, right? So we divide it into segments and then say between the bus and each line or between the lines, you will put one breaker, right? So always between the two nodes, there will be a breaker. So now what happens? If there is some sort of a failure in this bus A, quickly 52, see, you can see that normally closed, everything is normally closed. Everything is normally closed. So what happens is that these two guys will operate for a bus A fault. You can see that, which means that still none of these lines are disconnected. Then if there is a fault on bus 2, then these two will operate, but none of these lines are disconnected. Of course, if you are so unfortunate, then both of the buses will have some errors, but very rarely, right? So, but one of the major advantages here is that none of the customers lose power when there is a bus fault, and you didn't have to use large number of breakers as well. It's only not 2, right? Only a 1.5, right? So that is very attractive feature of break and half. So each of these buses will have their own protection schemes, and then usually we will come to that. All those protection schemes are differential protection, as I said before, because you are measuring the current difference. So always bus protection is associated with a differential protection scheme, not other schemes. The last one is called ring bus. Ring bus is also quite interesting. It's basically a ring. See, this ring is the bus. The bus looks like a ring, and then between each node, again you will have a circuit breaker. It's very similar to that previous one, but then the ring buses are quite attractive because of its higher reliability and the flexibility. Right? You can see that here. Like, let's say, but even after taken out of operation of one of these, let's say, circuit breakers, if this is open, then still you can provide the power through other part of the circuit. Right? So it's very, very reliable technique. And what else? Yeah. And then also, in this configuration, you don't need a separate bus protection at the line positions. So you don't require any protection at this location. The reason is that you can see that the measurements are done across these two, and then this line is covered, and then across these two, this whole section is covered. Across these two, all this section is covered. Right? It's put it in such a way that, can you see that this one overlaps this one? Right? So which means that, let's say, errors here in this CT for some reason will be covered by the other CT, set of CTs. Like, let's say if there is some leakage here, that will be covered by these two. But if there is a leakage on this one, that will be covered by these two. So it's a sort of a mutual connection is there. Like, this guy will look after him, and then that looks after the other guy. Right? So that is another advantage here. Right? This is very, very common in the high voltages. And then sometimes that when you are looking at this bus configuration, instead of only looking at the bus, sometimes the transformer is also included in the protection scheme. So for transformers, you will learn that differential protection is very common, but for the bus also you can include the whole zone like this as the differential protection zone. So what we do is that we look at the current leaving this in these feeders, and then compare it with the incoming current to that feeder before the transformer. So then definitely there will be a turns ratio issue. You need to consider those points. Like, let's say incoming might be 100, let's say 1000 amps, but outgoing could be 5000 amps, right, in the real world because of the transformer ratios. So we need to consider those factors when you are looking at these sort of things. By considering all these different types, cost and reliability can be tabulated like here. See, radial is very cheap, and then double breaker double bus is the most expensive, and then breaker and half 1.45. Right? So ring bus 1.25, so it's smaller than the breaker and half. Right? But the reliability is number one in the highest reliability, and then it comes down to the lowest. Right? So the middle is this ring bus and the break and half. That's why that it is common in most of the cases. So when someone is calculating them, probably, have you heard about PSI-D and PSI-Phi in other courses now? Yeah, so those like duration per customer and then frequency per customer, when there's a power loss, you need to identify that, all those factors to determine which one is suitable for a certain substation. And then, what are the possible faults in the bus bar? Human error is very, very common. What is human error? What is the most common error that could be possible? The possibility is that, say, you are doing some maintenance on a bus bar. If you are doing a bus bar maintenance, then you have to put a earth, right? Without doing earthing, nobody will do any work in the high voltage sector. You need to connect the earth to the bus bar. And then sometimes they forget to remove it before you switch it on. Then huge short circuit, right?
And they take all the spanners and all.
Yes.
And they forget to take it.
Take it. Yes. Right. So human, and then the spanners and all those metallic tools. Sometimes leave it on the bus bar, right?
I have faced some
Did
snake
you?
got to that.
Oh yeah, that's a second. That's a small snake is very common here in Australia.
So you should not keep any holes open in the breaker sections.
Right? And then the equipment failure as well sometimes, right? Some equipments fail, and then because of that, they're connected to the bus, and then that could have some short circuiting issues and all. But as you said, small animal contact, right? I had some photos as well, that sometimes the python or snake could short circuit these things, right? So those are the real practical world issues, right? You can't stop them. That's why the protection is important. And then the other thing is the wind-driven objects. Like sometimes that if it is heavy wind and then some objects flew and then short circuit the bus bars, so that could happen as well. So these sort of things which you can't, human errors probably you can minimize, but other things that it's really hard to avoid them. And therefore, the installing bus bar protection and then what type of protection has to be it's a case by case thing. And then when you are designing it, it has to be like, let's say, as I said before, how many customers will lose the power, what is the economical impact, and not only economical impact, but let's say whether the what sort of load is connected to these feeders, right? All those things has to be investigated. And then finally, and also that if certain area has redundancy, like as an example, the power is coming from another feeder as well, another substation, and then it's a sort of a ring connection, right? Then probably you don't need to have very high reliability for a certain substation, because another substation can look after the same area. So therefore, if the redundancy is there, you can reduce the cost as well. So before looking at these bus protection schemes, you need to identify what are the components associated with the bus. So typically it is just the bus bar, and then these are the disconnectors, and then isolators, we call it as isolators as well. And the number one is the breaker here, right? And then sometimes, why do you have this sort of isolator? Pardon? Across the circuit breaker, you have another isolator here. That's called the bypass isolator, where that sometimes if you want to do some maintenance of the circuit breaker, you need to use that one, right? You need to short circuit it, right? So it's so that let's say still you may be able to divert the power, right? This taking out of operation, and then you short circuit this. So there are these sort of different configurations are there. And then of course you need the CTs. Remember, the CT measurement usually is after the circuit breaker. Why is that? So that is the only way that you can identify every fault before the circuit breaker. If you put somewhere here, then who will identify the faults in between the CT and the circuit breaker, right? Because circuit breaker has to disconnect for any faults within its zone, right? So to do that, you need to put the CT beyond the circuit breaker, right? Not towards the bus, away from the bus. We will learn mainly 3 different types, considerations here. When you are looking at the bus fault, main things are the high fault current, severity of the fault strip, and finally the security. Those 3 has to be very, like you have to look at it very carefully, because high fault current, definitely you have connected large number of sources and then circuits basically. When you have high fault currents, then it creates a lot of forces, because magnitude of the current is very high, magnetic field is high, therefore that creates a lot of forces on the could be transformer winding or even the bus bar, right? Very, very high forces. And then the other important thing is that, say, when you are having very, very high magnitude of short circuit currents, CT is going to saturation. When the CT goes into saturation, we are having a problem because we can't measure it, right? And then we can't identify the faults. So that is another thing that we need to consider. So sometimes that, we as human beings, that when there is something which you can't avoid, then you use that to as some sort of let's say advantage. So in sometimes that we use, I will come to those CT saturation to identify the faults. So then you don't have any problem, right, of CT saturation. So that is another, way of identifying this bus fault. So we will come to those things. Of course, severity, I discussed, like large number of circuits can be interrupted, and also if, let's say, large number of generators are disconnected, that may have some impact on the stability of the system. Whole system could be collapsed. Therefore, we don't want to remove the bus and then the whole circuits completely switch off. We don't want to happen that as well. Complete switch off is not the solution. Yeah, if you are looking at the bus protections, then we need to look at measuring boundaries and tripping boundaries. As I said before, you can see that say in this particular case, this is the tripping boundary, right? That is the point that you tripped the circuit, but then your measuring is here, right? So this particular case, bus zone measurements are done on these ones, not using these CTs. You have other CTs, definitely. You have CTs just before the circuit breaker as well. That will probably help you to identify if something happens only, if you know that the issue is in this circuit breaker, you can use these 2 CTs to identify. But when you are looking at the overall picture for the whole system, for the bus zone, protection schemes, the measuring zone is this one. But then these measurings, what is that measuring? This measuring boundary is for the line. See, this CT is doing the measurements for this line protection. This CT is doing the protection, measuring for the bus protection. And then in this particular case, that is divided into 2, like bus 1 and bus 2, right? It's the same thing here, right? Because if you are looking at independently, this is the bus zone measurements, bus 2 zone measurements, and then this is bus 1 circuit breaker, bus 2 circuit breaker, right? So remember, as I said, breaker is overlapped by the bus and network element protective relaying zones, avoiding blind spots. It's very, very important to avoid the blind spots in the when you are looking at the protection zones. Yeah, that's why measuring boundary zone is, or the say boundary of the bus protection zone is slightly larger than the tripping zone. So the tripping is here, this one is there, right? Remember that those are very important points when you are designing a protection scheme. So three different schemes we are looking at for bus protection. Main one is differential, and then other two are zone, interlock, and time coordinated, which I'm going through the differential quite a bit. So why differential protection? Because we can't use the impedance protection, because the bus impedance is almost the same everywhere. There's no impedance differences, right? So therefore impedance is not going to work. And then the easiest way is that you are looking at a certain zone, and then if there is a current difference between incoming and outgoing, then it is easy to identify. So the differential protection is the ideal as we have current entering the system and then the leaving the system can be very well defined, right? Because they are the feeders. Therefore, differential protection is the ideal one for this one. So it's very easy that you are looking at the current entering the zone and then the leaving the zone. So, but there are different categories of differential relays which you can use for these sort of measurements, right? Usually the simple differential relay, which is called differential connected overcurrent, you just measure the difference. And the second one is the percentage. Probably you can remember I mentioned about it in the last two slides of overcurrent relays. That is called percentage restrained or biased differential protection scheme that can be used. Then there are three different things called high impedance, low impedance, and fall pass. Right? So those are the last part of this one, which is quite important. High impedance, low impedance ones. Especially the high impedance one, we use the CT saturation there. We will look at those things in detail. So this is typical bus protection scheme. You can see that you measure the input current, measure the output currents, and then see the difference. If there is any difference, then there will be a current going through this relay, and then it will identify, and then it's say that yeah, there is something fault in the bus, therefore I1 plus I12 plus I3 is not equal to I. Then operate. Now how do we select the CT ratios? That is another important thing for these ones. Say typically what we do is that we look at the line current ratings, right? Oh yeah, this is 1000, 2000 and 3000. Then what I can do is, yes, this is 1000, therefore I can use 1000 to 1, 2000 to 1, 3000 to 1. Now what happens? Let's say, okay, now you connect them in a way that you can add the currents going through these ones. So this is 1 amp, this is 1 amp, because 1000 amp, 2000 amp, and then this is 3000. Now 2 amps is coming here through this one, and then in this configuration 1 amp is coming, right? So what happens to the rest? This is 2 amps, this is 1 amp, therefore a 1 amp is going through relay. If your relay is set to plug setting of 0.5 amps, then definitely the relay will operate. Is it? That shouldn't operate, right? That is the problem here. Now, see, so it is not advisable to use the line ratings to select the CTs. What we need to do, we need to look at a different method to select the CTs. So typically, as you see here, I put 3000 to 1 in all lines. So because then all of them, like you can see 1/3 of amp is going through here, 2/3, addition of them is 1 amp coming here, and then this one will produce another 1 amp. So that 1 amp, 0 ampere current. So the series ratios for all buses should be the same. That is very important here. If there is no transformers in between, right, you go for the same CD, but remember, we can't go for the lowest, right? We should go for the highest rating one. So that is an important thing to remember when you are selecting CTs for bus protections. The other important thing is that, as I mentioned about this, that the accuracy and reliability of differential protection, that depends heavily on CT accuracy. If the CTs are accurate, yes, they are giving you good results. Now, if you think about situation where a fault occurs just at this point, right? Now, if the fault is in this point, there's a huge amount of current going through these CTs in that line, right? So, just double check how many times we have only 2 leads, right? I will just stop here because it connects with the next part, right? I don't think that I can continue beyond 9:50. So I'll stop this on this one, and then how many more slides? I have 23, another 20 slides. So what I'll do the calculation of voltage transformers on Friday, and then I'll try to finish at least the important part of this section, and then Tong will cover some questions for the mid-semester exam. Okay, thanks a lot. Any questions? No? Okay then, thanks a lot. See you on Friday. And then remember, we have the labs. Right? I think it's starting today or? Today, yeah. You have today?
Some of the students might have Thursday.
Yeah. Do we have labs on Thursday, or I have to double check? I'll double check.
Have days
Because then next week, Thursday, no problem. I think no, so I can't remember the lab days. Okay, I'll look at it. Thanks. Okay, bye. Hello.
How are you?
I'm good. I got one student today.
Last week I had a tutorial on Friday. That was the first time that I gave the lecture all by myself. No one in the room and no one online. Imagine.